Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. We'll be taking a look at the Keithley 2470 source meter. Now, this particular unit is very similar to the other source meters I have reviewed in the past, but this one is a high voltage version. And I think it's worthwhile spending a little bit of time and understanding the difference between various SMUs that Keithley currently offers, and then we're going to do a quick teardown and a lot of experiments that I have built to test and see how this thing operates, particularly its high voltage capabilities. So let's get started. So all of the Keithley Graphical SMUs are essentially the same from a programming and user interface, but they differ in terms of their power envelope, and that's because the optimum dynamic range of these instruments are shifted around and placed in different regions so that you would pick the one that's most suitable for the kind of application you're dealing with. The 2450, which I've also reviewed, is basically an all-around instrument. You can see its power envelope, it goes to about 200 volts and to 1 amp, and you can use it in a really wide range of applications. The 2460, which I've also reviewed, was introduced for very high power application when you needed a lot of current, so it goes up to 7 amps. It still maintains plus or minus 100 volts. Remember, all these instruments are always 4 quadrants, of course. Those are true source measure units. The 2461 is a unique instrument because not only does it have the same power profile as the 2460, but it has a dual 1 megasample per second 18-bit digitizer built into it, giving it a lot of new capabilities, including pulse support, and I've also reviewed that too. The 2470 now finally pushes the SMUs into a high voltage regime, allowing it to go to plus or minus 1000 volts. So this is now all of a sudden excellent for next generation semiconductor processes. For example, in gallium nitride design, you do want to have these high voltages and you want to stress test your devices and find out how they perform. And these devices are now very common, especially in high efficiency power supplies. So looking at the power profile of this one, the current is not very high depending on the voltages you select, and really I wish this 200 was actually a little bit to the left and maybe around plus or minus 500 where your current drops to 10 milliamp, and we will see some of that limitation in our experiment. But indeed these 4 instruments now cover a really wide range of applications, and the strength comes when you combine them. And we will do that in our experiments too, where we will combine the 2 of them and take advantage of the strength of each one depending on what it is that we are testing. So enough of that. Let's go take a look at the unit. And here is the front of the Keithley 2470. This looks essentially identical to all the other 2400 series SMUs with a GUI interface that Keithley has released in the past couple of years. It has a very nice capacitive touchscreen with big bright numbers, very vibrant, which helps a lot in the lab, especially if you want to look at it from very far away. USB in the front and a mechanical switch that completely turns the unit off. There are a set of buttons on each side, which I find to be a good choice in order to help you navigate in and out of the GUI depending on what's being displayed, and we will see that a little bit as well. The output enable, of course, up here, which lights up when it's enabled. There are a few lights in the back here, particularly the interlock I find to be very useful, because for an instrument like this that goes up to 1000 volts, you want the interlock to be something that's visibly available to you to make sure that your setup is actually correct. We also have force in and sense as well for a 4-wire measurement, and the chassis ground. There's also a button here in order to do front and back. This is actually a soft button, so there's some mechanical switching inside that enables for you to go from the front panel to the rear panel, and they probably have done this in order to not have to have the 1000 volt directly on a switch over here, which kind of makes sense. They have to do this very carefully using some other electronic methods. So from the front, yeah, we're essentially looking at exactly the same SMU as the rest, but the back of this unit looks different. And here's the back of the Keithley 2470, and it has some unique features. First of all, there are 3 ways to connect this instrument to the PC: GPIB for legacy support, USB, and Ethernet. Ethernet is particularly useful if you want to have this reasonably far away from your computer or connected to a network. There's also the digital I/O, which can be used with internal triggering or external software in order to have some interaction with the device and trigger on some event, for instance. But really my favorite interface here is the TSP link, not just because it spells the signal path, but because the TSP link allows you to daisy chain a variety of these instruments to each other, with a master instrument controlling everything else down the chain. So you only have to have one unit connected to a controlling PC, and all the other units in the TSP chain are simply connected together and work the same way. This is fantastic because it works with the Kickstart software as well as with the scripting software to do some pretty powerful automated measurements. And I've shown some experiments using this TSP link in my previous videos when I did some review of the 2450 and the 2460, and of course we're going to do some of that in this video as well. There is also the interlock here. Interlock is particularly important for an instrument like this, because when you go to 1000 volts, you need to have some safety in place in order to make sure somebody doesn't accidentally touch a setup that's live, for instance. And usually those setups are enclosed in something that trips the interlock if it's opened, and that way the output is disconnected and you don't accidentally get zapped with 1000 volts on your device under test, which is quite good, and we will see that in our setup too. Then we have 4 triax connectors in the back. So the use of the triax connectors for this instrument is also pretty important, because when you go to 1000 volts, measuring currents in the orders of nanoamp actually become quite difficult, because everything leaks at these high potentials, and these strong electric fields across conductors can cause a leakage current to go through. In order to solve that, you have to have a guard voltage with you to basically stop the flow of electrons across the conductor, and that is done using these triax. So if you look at the force here, the inner conductor and the second conductor are connected to each other, but on this sense, the middle conductor is connected to the force and the inner conductor is your sense, which means that the sense port is shrouded, covered with the same potential as the force, allowing the reduction of the leakage between those two ports. So you can still measure currents in the picoamps, hundreds of picoamps, and not have to worry about the leakage, when you're running at 1000 volts. This is crucial, and without it, you just simply won't be able to do that. So you can see it's really well thought out. Again, to be expected, Keithley is the master of making precision DC measurements, so that, of course, translates to really great design as well. So now let's go ahead and do some really basic tests with it, just so we can get a look at the GUI, and then we make our setup more complicated. So let's take a quick look inside this instrument and consider some of the design challenges. Now, this is a high voltage instrument. Now, creating a high voltage power supply inherently is really not that difficult, but to create one that has low ripple becomes much harder, especially with the precision of, let's say, a 6.5 digit meter that would be accompanied with it. To then design it to cover 4 quadrants becomes that much more difficult, because you need particular switching and analog circuitry to support all those different functions. That's a whole other game. That's why SMUs are typically quite a bit more expensive. Then on top of that, you have a very confined space here, because these SMUs all have to have exactly the same form factor, regardless of what kind of power dissipation they have, what kind of voltages they support, and so on. So that means that this thing has had some really remarkable engineering going into it to be able to make it fit into the space that you see. Now, much like the other SMUs, it's broken into several functions in different PCBs. Here now we have the added complexity of the high voltage being present as well. We have a main digital board. This main digital board has to be really well isolated from everything else, particularly from the high voltage circuitry, because it has human interfaces at the back where you can connect Ethernet and GPIB. The safety of something like this is really, really important. And you can see even some shielding put additional on these cables to make sure that they don't, for example, get nicked by something and then get connected to it. So on this, there's a lot of computation. There are, in fact, 2 MPC 5125 NXP 32-bit microprocessors on this already, so there's a lot of computation connected with several flash memory and so on. There's even a Spartan 6 on here and some circuitry to support the GPIB, Ethernet, TSP, and USB interfaces. This connection over here, the ribbon from here to the front, connects the entire digital portion to the front. Now, inside this display, there's a full computer, and all the GUI to control the software as well as the LCD and everything is actually built into this in a really small, narrow form factor, which is quite amazing. This also means that this portion is constant among all the SMUs, and then it just interfaces simply with a computer on board, which is optimized for the particular function of that class of SMU. It's a nice design. We see a big transformer here, undoubtedly part of the high voltage class of circuitry that's connected to it. The fan over here blows across the heatsink on the other side, which we will see. But now if you imagine, here are the triax connectors in the back. So they're connected to another PCB over here. That PCB has to be really well isolated from this, as I described earlier. But also the placement of all the other power supply components become critical. From the top over here, we see a bit of a hint of the circuitry at the bottom where the transformer is, and various cutouts in there to handle the really high voltages, as well as isolation and several analog circuit design techniques that goes on to PCBs of this class. There is something interesting here to note. If you look over here, there is a plate, a conductive plate that's sliding underneath this, presumably separating the high voltage power supply from this digital, and is connected to some voltage on that board. Typically they do this as a guard. You can create this for a variety of reasons. You can protect from arcing, you can create a lower leakage path by bringing a potential between several boards. There are a lot of these little tiny things on this board, that must have taken forever to design. So I'm curious to see as we look more and if we can discover some of them. Let me just flip this over here a little bit, just give you an idea. There we go. You can see this is the main board, which we have the triax connectors to it, several isolation circuitry. There are plates that run across the whole thing, which are also biased at particular potentials. You can see even here with these standoffs, they have put some isolation around them so that to really minimize the chances of anything arcing onto them and jumping onto them, because that would be really bad. It will make its way into the chassis and into the digital board on the other side. So yeah, there's some pretty cool design in there. Let me go ahead and flip it further. So in the back of the unit, we see some more hints on the high voltage design that's gone into it. So we see some ferrite beads here with some cables wrapped around it, and this could be a makeshift transformer for picking up some of the pulse capabilities and so on, or some measurements, or it just simply could be for filtering purposes. There are triax and coax cables wrapped all around it. We have some Rubicon capacitors nicely connected together with silicon for anti-vibration, big relays, presumably switching between front and back or some of the other high voltage functions. Here's the fan. Now here's the main power supply that just powers all the digital. You can see how nicely it is in its own cage. On the other side of this fan, on the other side of this, close to the screen where digital noise doesn't matter so much, and therefore isolating everything. Really nice design and how they've thought about all of this at the same time. Now look at this board in the back and look at these cutouts. So here's a pin, a standoff. Look at a cutout around it. It's beautiful. And around this pin you can even see further cutout, as well as the cutout of the metal too. All of this isolating and protecting. I really like this one. It looks like to be some switches or transistors on the other side that might be part of how they switch either from the front to the back, or maybe they switch the polarity to get the 4 quadrants. It's not clear because the schematic of this is not available. We even have guard traces on the outside as well as cutout. This is really held by very few tiny places. It's really quite nice. The design of this is obviously, this is Keithley, to be expected, of course. The main heat sink over here that the fan runs also nearby. This is also connected to the chassis to get heat out, filter on the incoming power. Now I would love to take this out further and so we can see the different layers and what's connected, and I may do that in the future, but I want to jump into the experiments and not disturb this thing's calibration for now. But you can let me know in the comment section what you think, but let's do some experiments and see how it performs. So if you have watched any of my previous Keithley SMU reviews, you'd be quite familiar with the GUI interface these instruments have. In fact, this is the same GUI that's running on the digital multimeters too, which creates a nice consistency across all the instruments. Another thing they've done with these units that I really like is that whenever there is a firmware update to any of them, there's a bug fix or a feature upgrade or any improvement, there is a firmware release for all the instruments at the same time. This prevents a fragmentation that can happen between different versions and some features not being available somewhere else, or some bugs existing in some of the units. That's really great, and it must have taken quite a lot of effort to bring that unified code base to all the instruments they have. The instrument has also improved over the years, especially the GUI functions and features, and the speed in which the instrument operates has become quite a bit better. So it has the same basic interface it used to have, but all different settings being accessible with a swipe to the left or the right. Fully programmable, of course, as we will see. And I'm going to go ahead and change this from 6.5 digits to 5.5 digits, and you can see you can easily go back and forth. So it's really basic and quite intuitive. Now, I don't want to go through the GUI again because we've done that quite a few times. What I want to do is do some basic experiments, especially taking advantage of the fact that this guy can go up to 1000 volts on 4 quadrants, and we should be able to get some interesting results out of it. So let's try out the interlock just to see how well it performs and how quickly it can extinguish the output, because it is an important safety issue here. So here's the voltage right now set to 0 volts. I'm going to go all the way to 1000 volts. There you go. So here at 1000 volts, you can see that we are measuring 1000 volts, and this is reading back 0.99998 kilovolts, which is exactly what it should be. So right now we're at 1000 volts, obviously quite dangerous, and the interlock light is on because I do have an interlock switch in the back, which is this little switch over here. This of course doesn't have 1000 volts on it. This is just a digital logic to turn it off. So I'm going to flip this and see how the output goes away. Here we go. There, done. And you can see it collapses the output right away down to 0. Remember that this instrument has a 10 megohm interface, the fluke of course, which means that it's not being discharged through the fluke, but rather is being handled by the instrument itself, and you get a warning telling you that the interlock has been tripped. This is really important, especially in high voltage test setups. So let's start with a really simple experiment. I'm interested in measuring the leakage current of this capacitor decade module. Now this particular one is fairly old, but it does allow me to go all the way up to 600 volts. The thing about capacitor leakage is that that is a function of the bias voltage itself. As the electric field gets stronger across the dielectric, more and more electrons are allowed to jump across. This leakage is pretty important and also tells you something about the health of the capacitor, especially at high voltages. And it's important to characterize them and stress them and find out how they behave. So I've taken the back of this off, so you can see what's going on. It's a really simple unit, hand soldered a whole bunch of capacitors which you can adjust with various switches. So let's go ahead and put this at its maximum bias voltage and see how its leakage changes as a function of biasing. I'm going to close it back up and set it up. So the capacitor is now connected to the SMU, and I have the SMU set to 10 volts. Let's go ahead and enable the output and see what happens. There it is. So under this condition, you can see we have 10 volts. We're essentially in the noise of this instrument, and there's some algorithms with the auto ranging that sometimes causes this limit to show up. I've spoken with Keithley about this. I think they can optimize this a little bit better. Depends on whether this is an auto range or not. But right now we don't really see much of a leakage because the voltage is so small. I can try another position here. Now in this position I do see considerably more leakage, but sometimes in a setup like this, the stray current that can be induced by the wires and everything else, especially when you have a module that does not have a triax connector, can give you some false readings. So it would be nice to crank up the voltage to the maximum so we can get a nice clean reading. Let's go back over here. I'm going to go ahead and change this from 10 volts to 600 volts. That's the maximum this capacitor decade is rated at. There it is. So on this setting, we can see that we're jumping back and forth between the 10 nanoamps, sometimes 100 nanoamps range. The capacitors are going to charge up, and sometimes there is a bit of a dielectric absorption that happens. The charge gets trapped inside the dielectric, and eventually this will settle down. So we have about a couple of nanoamps of leakage on this setting. But if one of the capacitors in this module is faulty, we should be able to get a much more clean reading. So we go back to the last capacitor and check it out. Now we have 6 microamp at 600 volts. That's a big difference between the two positions of this capacitor. And as you saw, there are multiple individual capacitors in this, and it is possible that one of them is more leaky than the rest of them. By being able to measure at a very high voltage, you can differentiate that difference and stress test the capacitor to the edge of its limit. So it seems to work quite nicely. And go back to the other setting, and you can see the current will then rapidly drop off, and this will once again settle. You can also go to the measured curves over here and get an accurate reading, of course. And as you switch between the different regions, we're right over here at the very end. So if I switch over here, I can go ahead and maximize this and zoom in over here so we can see what happens. So that glitch that you see over there is right around where I switch. There's going to be a burst of current because the capacitor needs to charge, and when I go back down to the other setting, you can see that the current drops. So that makes sense. Now this is up to 600 volts. I do have a 1000 volt capacitor that I want to connect to the output and stress test the SMU for a moment. So here's another capacitor here. This is a 1000 volt rated capacitor. Everything is turned off, of course, and I have it directly connected to the front panel. Now again, normally you want to make these measurements using a triax. It's just harder to set it up so that it's in camera. So I'm just going to show it to you like this, but keep that in mind for your own measurements. So I want to charge this capacitor and see what the instrument does when you apply 1000 volts to something like this. So let me turn it down a little bit, just outside, so that I don't accidentally touch it. There it is. So let's go ahead and set it up. Here we go. I'm going to go 1000 volts. I'm going to turn on the output, and there it is. The capacitor is now charged at 1000 volts. Now this is a 0.1 microfarad capacitor, 10%, and you can see that it has a little bit of leakage associated with it, just like before, and it will settle down. But I'm going to do something that you normally cannot do with power supplies. In fact, it's often prohibited because it will damage the instrument. But the 2470 is a 1000 volt 4 quadrant instrument. So I'm going to go from 1000 volts while the output is enabled live. I'm going to go to a minus 1000 volts. That's a 2000 volt differential. As soon as I set this to minus 1000, the instrument would try to apply minus 1000. At a brief moment, there will be almost a 2000 volt difference observed in some of the nodes of the circuit. And yeah, that's a lot. And the instrument has to absorb that because the user can, of course, enter this number if they want to. So let's go ahead and give it a try. And there, look at that. From plus 1000 to minus 1000, no problem. You can see the current is now reversed, and it did that essentially instantly with a maximum limit of course 5 milliamp. And it's going to settle down to roughly an equivalent amount of leakage. There's going to be a slight difference in the two leakages. That's because one of the two terminals of this capacitor is on the outer casing, so the negative side is on the outer casing, and when you swap the polarity, there may be more charge escaping from one surface versus another. maybe some differences, minor ones. But yeah, this is pretty amazing that you can jump between 1000 to minus 1000 without any issues. We can go to plus 1000 once again. Okay, and there it is, no problem. Yeah, quite impressive. A lot of protection circuitry has to be in place for something like this to work. Let's now use the Keithley 2470 to measure some protection components. These components are very common in power supplies and other devices that have to clamp down on a voltage potential difference that may exceed what is specified. So we have two different devices I want to measure. I want to see if the 2470 can reveal some of the subtle behaviors of these components. So here's a Varistor. This Varistor is directly connected again to the output of the SMU, and we're going to do a sweep and find out its IV characteristics. A Varistor is essentially like a diode, but it's a diode in both directions. So we should be able to use the multi-quadrant feature to characterize it. And at the same time, these Varistors have very high voltage responses, as to be expected. They are protection devices after all. So you cannot measure them using traditional SMUs. You need something that goes to high voltages. So let's try it on this one. We can use the built-in features of the SMU to set up a sweep. So I'm just going to go under Menu. I'm going to go under Sweep here, and I'm going to build my own sweep. So this is a high voltage device. Let's start from, let's say, 750 volts negative, and go all the way to 750 volts positive. So that's a 1500 volt sweep. I'm going to step by 5 volts at a time, so it goes a little bit faster. Everything else we're going to leave as auto. I'm going to turn this off so it doesn't stop on a limit. I'm going to change the source limit here to 5 milliamp so that it would put as much as 5 milliamp into the device. Now remember, 5 milliamp, when there are hundreds of volts across this and when it triggers, is actually quite significant. So I'm going to go over here. I'm going to hit generate. It's going to generate that and put it into the trigger function of the instrument. So as soon as you press trigger, it will launch it. Let's go back to home. Well, let's change this into a 10 milliamp range so that it runs faster, since we're not interested in measuring nanoamps anyway. So now as soon as I hit trigger, it will run that sweep for me. So let's go over here. Let's change this to 6.5 digits. We get a little bit more digits over here, and we're over here. And these are all data, of course. Let's go trigger. There you go. So right off the bat, it looks a little bit strange. So it's running. There we go. So now we're in the almost at 0 volts. There it is. This is the voltage at the bottom. So it's running. It should soon go above 0 volts. There you go. 120 volts, 300 volts, and it should trigger from the positive side. There it is. So positive side trigger, and you can see it's still running. It's not finished yet. There we go. So we get a very classic Varistor response. That's what we were expecting. So let's go ahead and zoom out, and let's take a look at this graph. So at the bottom, obviously, we're clamping the voltage on the negative side around minus 500 volts or so, and the positive side at plus 500. But I set this instrument to go all the way to 750. So what happened in those situations? Well, we can zoom into here very nicely and see the effect of what happens. If I zoom in further and further. Now, how do we interpret this data? Well, what does this tell me? This tells me that as soon as the instrument hit about minus 492 volts, the current in the device was already at minus 5 milliamp, which means the Varistor had already triggered and clamped the voltage down at around minus 492 volts. So what is the meaning of this line going right? Well, that's actually a thermal effect, because as soon as the Varistor has triggered, the instrument is still applying a voltage, but it's already limited to 5 milliamp, and therefore the voltage is clamped to 492 volts. At the same time, the device is warming up, which means the voltage across the Varistor is changing as a function of time now, because it's getting warmer, and therefore the voltage is dropping. So you can see this really subtle behavior of this Varistor by looking at it this way. Now I can do exactly the same thing on the other side. I can maximize and go over here and look at this one, and you can see exactly the same behavior once I zoom in enough that indeed the voltage continues to rise from the other side as well. Now you can look at the data in a few different ways. If I go over here, instead of measuring versus IV, I can measure as a function of time. Now once I measure time, then you can see a much more familiar plot. Over here, the current is limited. So this is now this is time, not voltage. So the voltage has been decreasing down to 750 volts negative, but it's being kept constant by the current limit of this unit. And then once we pass the trigger point of the Varistor, we come back to 0, and then on the other side, symmetrically the same way. Now it's really important to limit this. If I didn't have this 5 milliamp limit, we would be dumping a huge amount of power into this Varistor. It already gets quite warm at the edges of this sweep, and then that Varistor would eventually die. These are limited to a particular power consumption and dissipation. Now, another thing you can do is you can go under menu and you can go under histogram. Of course, you can look at the histogram, but if you go under the reading table, you can actually see this plot as a function of time, and you can go across it. It also has acceleration in the sweep, which is quite nice, and you can go over and see the voltage here being clamped all the way when the current is at 5 milliamp. There's a couple of things that I think would be really nice to add this to this plot, for instance. First of all, the source voltage is written, that's being measured. It would be nice to put another column here that says the applied or the requested source voltage, so that you can see them next to each other, and that is easy to see what voltage is being applied and what voltage is actually being measured. So that, I think, is a feature that would also be very useful to be able to apply to this plot. So when I go under the data, and I should have another third option here that would allow me to plot as a function of applied voltage. And then whenever the applied voltage is clamped, you can change the color of the plot to be red, for example, so that you know that it is not being applied. So a couple of minor adjustments here, I think, would go a long way. But just think about what we did. We applied an entire sweep, did all the characterization, saw these subtle behaviors all within the GUI without doing anything. It's all built into the instrument, which is one of the powerful features of the 2470. So here's our next protection device. This is a gas discharge tube, and this operates entirely differently from how a Varistor works. In fact, it's not even a solid state device at all. It consists of two electrodes separated by a certain gap, and inside the gap is trapped gas, which is allowed to ionize once the electric field across the two terminals exceeds a certain amount. Now, once this ionization starts, a huge amount of current is allowed to flow through the gas. This is the principal operation of fluorescent tubes and neon tubes and even camera flashes. Without this, we wouldn't be able to make those kind of components neither. Now, the advantage of this is once the ionization begins, the voltage is collapsed down to a much lower value than the starting ionization process, and therefore the voltage can be clamped way down and protect whatever devices you're using. They can be quite useful as a result. They have some disadvantages of their own. They're again non-solid state, but they are used all over the place. This is a 3-terminal device. We're only using 2 of its terminals. So let's check the settings. I have basically exactly the same settings as before. We're going to do the same sweep, and we're going to see what happens. Now, the difference here is that once I start this sweep, it starts already at minus 750 volts. It means that this guy is going to trigger right away. And as soon as it does, it will clamp the voltage to well below minus 750 volts, and we'll see some pretty interesting IV characteristics. Let's give it a try. Let's run the sweep now. Now keep an eye out on this, because even though this looks opaque, you will be able to see the arc going right through it. You can see it optically actually. So here we go. I'm going to press trigger. As soon as I press trigger, look at that. You can see the spark already in there. Now keep in mind that the instrument is trying to apply minus 500 or 600 volts, but it's only getting about 50 or 60 volts because this is already ionized. Now once it passes a certain point, once it drops below the certain voltage, then the ionization stops. Now it's allowed to go higher and higher in voltage. And look, it's going to hit about 600, and it began again very strong, and it stopped. Let's take a look at the curve. The curve is going to look really interesting. Yeah, look at that. That is very interesting. So there are a lot of things happening here that are at the same time acting both on the SMU's limitation as well as measuring this gas discharge tube. So first of all, when this thing ionizes, the amount of current that can flow through it can be really high. At the same time, the Keithley is trying to limit that to a maximum of 5 milliamp. But there's a time constant involved here. When this guy limits the current and the voltage drops, the ionization stops. So this guy then goes back and applies a high voltage again, and the ionization begins. So it then ends up being a series of pulses that are fairly unpredictable. And I'm very surprised that the SMU does as good of a job as it can to produce a plot like this, which is what we would expect to see from a gas discharge tube. These clusters of varying currents around this ionization voltage here is exactly what I was describing. It has to do with the time constant of the SMU as well as the gas discharge. Once we're below that, it jumps to 0. You can see around minus 200 volts, and then now the voltage is now free to increase all the way to when the gas reionizes again, and that threshold, that trigger voltage, is 600 volts. As soon as that is reached, the gas begins to ionize, the current flows, the sparks are jumping, and it jumps all the way back to an equivalent voltage symmetric to this point. So you can see here at 0, we are actually about 50 or 60 volts. Over here, we're settled at around 200 volts. So you can see that this IV characteristic is actually quite tricky to plot and quite tricky to measure because there are multiple things that are acting on top of each other. There's also the fact that you see a difference between these 2 points around the 0 is because there is hysteresis of this device too. This device will have a hysteresis effect under increasing voltage versus under returning voltage. You will have 2 different trigger points for where the ionization begins and ends. These are very interesting and unusual devices to measure. But again, I just wanted to show you that the 2470 can reveal a lot of these device properties by just using its own built-in functions. And if you want to measure those different points, we can put some markers on this and put a marker over here on this point and put a marker over here on this point. You can see the trigger on the positive side is sitting at around 611 volts, and on the other side is around minus 200 volts. And if you have a complex plot, you can have vertical or horizontal lines and move them around. You know, it works reasonably well. Obviously the screen is a little bit small, but in terms of catching which one you're trying to move around, I think they've done a really good job with the GUI. And of course, one of the advantages of the Keithley SMUs is that they are designed to work together. And this also allows you to mix and match them in your setup to take advantage of the strength of each one depending on what it is you are trying to measure. So for instance, here I have the 2470 at the bottom and the 2450 at the top, which means that I am able to apply very high voltage when I need to, and I am able to measure very, very small currents when I need to using the 2450. And what I'm measuring here is an N-channel CMOS transistor. And this transistor has a very, very high drain to source breakdown voltage. It can go all the way up to 900 volts. It's designed to be used in very high voltage and efficient power supplies. So what I've done is I have connected its gate to source voltage to the 2450, because the gate to source voltage breakdown of this device is only 30 volts, and therefore we can use the 2450 to measure things like gate leakage with extreme high precision, and we don't need to go to very high voltages. But on the bottom, the 2470 is across the drain to source, which means that I can actually stress this device up to 900 volts if I wanted to, and therefore I can measure, for example, the subthreshold leakage when the device has a very large drain to source voltage across it. And by combining the two of them, I can make multi-dimensional voltage signal sweeps and then measure the IV characteristic of this device in a variety of situations. Now I can do that all through the GUI or so on, but I would like to do it using the Kickstart software, because that's where I can do some really fancy analysis of this device. And here is the Kickstart software, and at the bottom right you can see I have a live view of the instrument so that when we make some changes we can observe them. The last time I reviewed the Kickstart, it was quite a long time ago, and I did it for the review of the 2450 and the 2460, and it has gone through a lot of iteration and changes since then, and it is also a paid license, which means that it doesn't come for free with the instruments. Just something to keep in mind. Now, under the apps section, because they've done so much work on the Kickstart since the last time, they've added a lot of different kinds of measurements you can do, and these are different licenses that you can purchase depending on your needs. There's also at the very bottom here an IV tracer. This IV tracer is an actual app that gets installed directly in the SMUs, turning them into an IV tracer. I'm going to save that for later, for a different video, because there's some really interesting things you might be able to do with the app development of these instruments, so we'll leave that for another time. For now, we're going to take a look at some IV characteristics. If I go under the Instruments tab, you can see that the 2450 and the 2470 are both recognized. So both of them are simultaneously connected to the PC using 2 separate USB ports. And while at the same time, you can connect the TSP interface to the back together in order to allow for really high-speed triggering. So you can't daisy chain them like you can do with this scripting using the Kickstart. You have to simultaneously connect it to the PC. So, well, I've already made one setup in there, so let's load that. And here is my setup. It's really quite straightforward. I'm using the 2450 as a stepper, so it's going to go through distinct voltages, and those voltages are from 2.5 volts to 4.5 volts in 0.2 steps. So this is the gate source voltage of our transistor. Naturally, by jumping between those two different voltages, several voltages, we will be able to plot the IV characteristic. But it happens that most of those voltages are actually below the threshold voltage of the transistor and just at the edge of the threshold, which means that we would be able to see its subthreshold voltage and its transition into being essentially forward biased. So let's go ahead and change the 2470 as well. So here I'm doing a linear sweep between 0 to 500 volts. So I'm really stressing the drain to source voltage, allowing us to see this behavior across a wide voltage. So if you want to make, let's say, an amplifier using this transistor in the subthreshold voltage with a very, very large amplification because of its drain to source voltage, we can see how that behaves. Now there is one limitation that I wish it was a little bit different. So the threshold for where the maximum current of the SMU 2470 jumps from 100 milliamp to 10 milliamp is at 200 volts. It would have been really nice if that transition wasn't 200, it was more like 500, because if I want to measure anything up to 100 milliamp, I'm limited to the 200 volt range. As soon as I go above that, I have to do 10 milliamp. So there's a bit of a limitation there. That's just the way they've chosen to partition those voltages. That's the limitation of the instrument. So let's go over here. So everything's already set up. You can see all the different settings. You can check exactly as you would do using the instrument itself, and in some cases even more so than the instrument. So let's go ahead and run this and see what happens. As soon as I press play, you can see at the bottom right here that the instruments spring into action and they begin to do the sweep. So at the top you can see a voltage of 2.5 volt is being applied, and at the bottom we're sweeping at about 260, 270 volts. Now if I go under the graph over here, the instrument would automatically begin graphing. Now this looks like gibberish because I have to be plotting SMU2 voltage. There it is. So you can see that at the very, very low gate source voltages, we basically have no current, right? It's essentially at zero. And as the gate source voltage increases, each of these lines running across, that's one distinct VGS. If you hover the mouse over it, it will tell you what those conditions are. So right away you can see some interesting properties emerge. First of all, the slope of these lines are increasing, which means that the output resistance of these transistors are actually changing. Not only they are changing, they're also changing as a function of VDS as a secondary order. So these devices have extremely high output resistance. That's why these lines are so flat. The output resistance is the inverse of the slope of these lines. As we increase VGS more and more, you can begin to see that the slope is changing. Now this is going to take a little bit of time, about 1.5 minutes. But we can keep watching it a little bit and look at the end. You can see it's beginning to pick up even more so the slope is changing. So the output resistance is a function of VDS, which is again a secondary effect for a MOS transistor. We're going to keep going again. This is going to continue as well. It's going to pick up even faster and faster. What voltage are we at? We're already at a VGS of 3.5 volts. We're getting pretty close to the threshold voltage of the transistor itself. Let's go and see what happens to this curve. Now really the slope is picking up. Remember, we are still only at 250 microamps, so we're really not burning a lot of power in this transistor yet. It's really not conducting very much. There you go. Now we're in the milliamp range, so these lines are now squeezed at the bottom. The slope is now really getting higher and higher. Here we go. Nice. It's going to do one more. That's a big jump. Now what we also expect is that the IV characteristic of this transistor as a function of VGS initially is going to look exponential, and then it's going to get into the quadratic region, and then finally into the linear region if the device is not fully saturated yet. So what is going on over here? Well, what happens here is that the device has hit compliance. It cannot provide more than 10 milliamp. This is what I was saying, that I wish it was a little bit more, up to 500 volts, so we could see this characteristic a little bit better. And as soon as that happens, the voltage begins to drop, and that the device is now conducting stronger and stronger. Therefore, the voltage across the drain to source is dropping faster. So at this point over here, you can see that the drain to source voltage is around 175, 180 volts, and it's already conducting 10 milliamp. At the next VGS voltage, we are only seeing one dot, and that's because the device is now fairly strongly turned on, and the current is just clamped to 10 milliamp at a voltage of essentially zero, because the resistance is now so much smaller. So this already gives us a lot of insight. We can export this, look at the slope, plot the resistance of the device as a function of VDS and as a function of VGS. But we can also change what is being plotted. We can go over here. Instead of the voltage of the SMU2, we can plot the voltage of the SMU1. So what we're looking at here is how the current in the transistor is changing as a function of the SMU1 voltage, as the gate source voltage. So at the beginning, you can see we're getting no current, nothing, beginning to see a little bit of current. Then it begins to pick up a little bit, and then it picks up, and then it shoots up all the way up. That's when the transistor is really turned on. Now, is this accurate? Well, let's find out. Here, around this point, it looks like is where the transistor begins to turn on, because we have a big jump in the IDS current. So what is this voltage? That voltage is 3.7 volts. Well, let's go to the data sheet of this part. Let's take a look at the threshold voltage of the device. Here it is, the threshold voltage, and check it out. Look at that. The threshold voltage is 3.75, which is exactly what we measure. So it matches the data sheet. Now you can go ahead and measure all of its DC characteristic using various combinations of these voltages and settings. And if you want to go to 100 milliamp, all you have to do is go back to the settings over here, and instead of pushing the 2470 to 500 volts, you simply push it to 200 volts. And if you do that, you can go ahead and change this current then to 0.1, just like so. Now you have a lot more current that you can push through the device. You just can't go to 500 volts anymore. Now all of this is basically the most simple ways you can use Kickstart because of the built-in apps and because of its compatibility to a wide range of instruments. You can even connect these to the oscilloscopes and use, let's say, the DMM functions built into them and a lot of other different instruments that Keithley produces, and you can have more than, of course, 2 SMUs, and you can do multi-dimensional 3 or 4 dimensional sweeps and do some pretty incredible measurements. And the data is available in a table, and you can export all that data out and grab them and process them, post-process them in a different software if you want to, and all of that is going to be quite handy if you have a lot of data that you need to produce. The GUI of this, it works reasonably well. It does some kind of funny things over here. Sometimes it doesn't, it's difficult to reach the curves you want. This idea of zooming in and out when you hover over something, it's a nice idea. I think that it's just so that you can have the biggest area to have for viewing things rather than occupied with the settings. I wish there was a way to not have them disappear, just keep them on the screen and a little bit a way perhaps to maybe make this larger, because I think it's difficult to work with it the way it is. But overall, it's a huge improvement over what it used to be in the past. I think they've put a lot of effort in it, and I think they even have bigger plans to make it even better in the future. So this is the Kickstart doing all of the communication for you in a GUI fashion. But what if you want to write your own script? Because that's really my favorite part of this instrument, because then you can do pretty much anything. So let's go ahead and take this, write our own script, and write an application that's totally unique and different. And here's the setup of our next experiment. We're again going to use a 2470 and a 2450, but this time I want to take advantage of the scripting capabilities that I can do on the computer using the script builder software to control this instrument using the TSP link in the back. Now, because I can write pretty much anything I want and take full control of this instrument using the script, I can write some pretty sophisticated algorithms. Right now I want to write an algorithm that employs feedback, meaning that I will measure something with the 2470 and I will take a different action on the 2450 depending on what I'm measuring. So you can imagine how this can be a closed loop system to take action depending on what is going on in the current setup. So let me focus in a little bit more so we can see what we're dealing with. So what I have here at the bottom is a source of butane gas. I can ignite this gas using this arc generator at the top. I can also activate the arc generator manually. There you go, you can see like that. So this will allow me to ignite the flame. Now once I do that, I have another set of electrodes at the very top that I can measure the resistance across. I can apply a very large voltage, let's say 750 or 1000 volts, and if there is a flame present between these two nodes, the resistance will drop significantly. Because of the ionized particles in the flame, it has quite a bit lower resistance than just air. And if the measurement tells me that the flame has gone out, I can activate the arc generator using the 2450 and reignite the flame. So basically like a safety system to make sure that if the flame has ever gone out, it is reignited so that there is no gas escaping in the environment. These type of closed loop systems are quite common, of course, in a lot of different appliances. So in this case, we're controlling it using the scripts and the 2450 and the 2470. So pretty straightforward, simple setup, but it shows the power of the scripting to run this. Let's go and take a look at the script. And here's the Keithley test script builder, and it has improved quite a lot over the years as well, both in terms of documentation and how well it operates. It comes with a wide range of examples too. Depending on which instrument you're using, you can start with one that is already written by the Keithley application engineers, and you can then modify it. It's very helpful to start from one of those. The Keithley test script builder is totally free. Unlike Kickstart, you don't need a license for that, so you can just download and try it out. And on the right side here, I have the help open, which is quite helpful because it gives you a complete TSP commands that this instrument support and really great examples of how to use each of them, and there's a rich number of commands available. So I just basically use this help in order to write this particular script. So remember what we're trying to do. We're trying to make a measurement with the 2470 and then take an action on the 2450. So at the beginning, all I'm doing is I'm setting up the 2470, which is monitoring whether the flame is present or not. So it just sets the voltage, sets the level, the limits, and so on. Really straightforward, actually quite readable too. And everything is object oriented. So once you create an object, so here is the flame monitor instrument is node 1, and arc generator is node 2, and you just have to basically put the name of that instrument at the beginning of all the commands, and it then knows which instrument is being targeted, so it routes the command to the appropriate one. Really quite nicely done. And here I have written a very basic loop here. This can be a permanent loop. I've only done here 1000 measurements where it checks it, and if it doesn't meet the value, then it will change the text and turn the arc on and turn it back off and check again. Really quite nice and simple, and that's all you really need in order to get something like this working. So you should really download this and play around with it. And if you already have an instrument, like I said, it's free, so it's quite easy to try. Let's go back and see how this operates. Okay, let's go ahead and start the script and see what happens. I'm going to apply the gas, run the script, and right off the bat, it's going to detect that there is no flame, and of course adjust that. You can see I have information, custom information here programmed in there, so the flame right now is okay, so it's not taking any action. I can blow out the flame like this, and it will immediately reignite it. It's actually really fun to play with. At the same time, you can collect statistics and find out what is a trend, how often it fails. You can create a trigger I/O in the back of the units and program that as well, so additional actions can be taken. And yeah, this is really quite fun. And this is with a very simple script. You can extend that and make it much more complicated. You can have many of these units in a row and program and control a lot of them in a chain and build very sophisticated algorithms, and all of that with just a few lines of code that you saw. And this is again just the tip of the iceberg. I've done quite a few other experiments using this script as well, which I encourage you to take a look at and see all the wonderful things you can do with these instruments. And there you have it. I hope you enjoyed this extensive review of the Keithley 2470. There are hours of material now available on my website on the various capabilities of these SMUs. I'm really quite impressed with these, and this is a big effort from Keithley to produce these and keep them all up to date and keep them all synchronized with each other in terms of firmwares and bug reports and everything that comes with them. There's a lot you can do with these things, and again, I'm not surprised that these are quite popular because Keithley is essentially the world leader when it comes to manufacturing these type of test and measurement units. Now, as always, if you like it, let me know, and if you happen to purchase one of these because of this video, please let Keithley know. I don't get any sales orders or anything from them because of this. This is just so that I can have a good relationship with them and be able to produce more of this cool content for you guys in the future. I'll see you next time.